Okay, welcome back to the session of Energy Laboratory. In this laboratory, we will be conducting the part B experiment. The aim of the experiment is to conduct the performance test and to draw the heat balance sheet on given four-stroke diesel engine. So here we will be available with the four-stroke diesel engine test rig. What we have to do is we need to conduct the performance test. Performance test in the sense how various factors are dependent on each other, how one variable is going to change the other parameters. Those things needs to be analyzed over here. Along with that, we need to plot heat balance sheet in the sense how energy distribution is taking place inside the engine, or how engine is utilizing the energy for various aspects. That needs to be drawn in the form of heat balance sheet. So that is what is our aim in this experiment. If we look onto the performance test, we have certain characteristic curves such as specific fuel consumption versus brake power, brake thermal efficiency versus brake power, mechanical efficiency versus brake power. These are the curves which we need to draw and then look for the performance of the engine. So this is the performance analysis curve. Next thing is operators that we are going to use. We will be using test rig, along with that stopwatch or stop clock is needed for us in order to conduct the experiment. So now directly we can move on to the experimental setup and then we can conduct the experiment. Go. Okay, here we are with the experimental test rig of a four-stroke diesel engine. Let us look onto the various components of the test rig. This is the engine portion whose performance needs to be analyzed. Engine has to be loaded with this loading device, which is nothing but the brake drum dynamometer, which is used to load the engine. And in order to supply the air to the device, so this is the chamber through which air is supplied. This chamber is going to stabilize the airflow into the engine. So these are the few main components which are required in order to look into the performance of the engine. We knew this is the four-stroke diesel engine. In case of diesel engine, only air enters into the cylinder. So air initially enters into this chamber through which the air enters into the engine cylinder. Thereby compression happens. Then fuel injector injects the fuel. Thereby combustion as well as the power stroke begins. Then exhaust will go into happen. These are the four different strokes that are performed by the engine. Now the developed power will be transferred to the flywheel and then the power will be supplied through the power will be transferred through the crankshaft. So in order to look into the performance of the engine, we need to load the engine. It will be loaded in an incremental or decremental order in order to look onto the performance of the engine. So this device is connected to the engine's crankshaft. So here we have the brake drum through which the load will be applied. The brake drum is wounded with the help of the rope, and then this rope will be tightened on either side. Thereby we will be looking onto the amount of load that will be applied onto the engine. So in order to look onto the performance or the conditions of the engine, we will be incrementally increasing the load of the engine. So one of the end will be tightened over here, and then by tightening this and by looking into the values, we will be directly increasing the amount of load that is supplied onto the engine. Next thing is the control panel, wherein we will be looking onto various other aspects. Here we have fuel supply measurement. So this is the tube through which the fuel supply will be measured. In order to measure that, we have distributor over here. So this is how the fuel supply will be measured, and here we have manometer through which we need to look onto the pressure with which the air is entering into the cylinder. Next, this is the speed indicator through which the speed with which the engine is running will be recorded. Next, this is the temperature indicator. At various junctions we have mounted the thermocouples. Those thermocouples temperature will be measured with the help of will be noted in this indicator. We have 6 different thermocouples. Those specifications are provided over here. T1 is the air inlet, T2 water inlet to the engine, T3 water outlet from the engine, T4 water outlet from calorimeter, T5 exhaust inlet to calorimeter, T6 exhaust outlet from the calorimeter. All these things are the thermocouple notations. So this is what is related to the performance of the engine. Next thing is you want to look onto the energy balance. How the energy supplied by the fuel will be distributed for various aspects. We have some more components over here. So here we are available with the two of the rotometers. One rotometer indicates the amount of water supplied to the engine side, and the another rotometer will indicate the amount of water supplied towards the calorimeter, which is present over there. So these two are going to get us the water supply to the engine as well as the calorimeter side. So next thing is we need to look on to the calorimeter through which the exhaust is getting passed. So this is the exhaust pipeline, and that portion, black portion, is the calorimeter. So initially exhaust passes on to the calorimeter, and then it will be sent out to the atmosphere. So now there also we have certain thermocouples. Those thermocouple readings are those thermocouples been shown over here. So for this exhaust gas calorimeter as well as these water measurements are required in order to look onto the energy balance that is happening inside the device. So this is how the components are arranged in order to look onto the in order to conduct the experiment. Okay, now we are starting the engine. So engine has to be started manually by cranking the engine. Now we are cranking the engine. Now engine has got started. Now we need to look on to the performance of the engine. Engine needs to be loaded now. Now we are loading the engine. Now fix this valve so that we can vary the load by adjusting this valve. Now spring is loaded on one side. Now we can fix the load on the engine by adjusting this valve. Now this is showing a reading of 4 and this is showing a reading of 7, and difference in these two readings will be the load on the engine for us. So we need to look on to the difference in these two so that we can get the load on the engine. So now here these two are the rotometers which are provided in order to look on to the
water supply towards the engine as well as towards the calorimeter. So water is needed in order to cool the engine. By looking into this or by fixing this, we can fix the amount of water towards the engine, and by fixing this we can fix the amount of water supplied to the calorimeter. So calorimeter water supply is required in order to look on to the amount of energy which is carried by the exhaust gas in the form of heat. So towards engine we have 6 liters per minute of water, and towards calorimeter we have 4 liters per minute of water. So these two methods are used in order to check into the water supply. Now we need to look on to the various other aspects. Here is the fuel supply indicator to us. Now we need to look on to the time taken for the 5 cc of fuel consumption. So now I am switching on this. Please note on the time taken for 5 cc consumption of the fuel. Now I am starting the timer from 5. I will be look on to the 5 cc of fuel consumption time taken. Okay, so now the time taken for the 5 cc supply of fuel has been noted down. Here is the speed with which the engine shaft is running. That needs to be noted down. And now we are available with 6 different temperatures that needs to be noted down here. T1, T2, T3, T4, T5 as well as T6. These 6 temperatures needs to be noted down. So temperature record as well as speed record as well as temperature indicator. These readings should be noted down. Now here we have the YouTube manometer with which we can look on to the pressure with which the air is entering into the cylinder. So knob differences, mercury meniscus distances should be noted down over here, so that we will get the pressure with which the air is entering into the cylinder. So now totally temperature, speed, pressure difference with which air is entering, and fuel supply, along with that load on the engine and water supply to the engine as well as calorimeter needs to be noted down for the trial. Let us start the second trial now by varying the load on the engine. Okay, now load on the engine is varied. On this side and on the other side, the values needs to be subtracted. So here we have 4, here we have 12. So 12 minus 4, 8 is the reading. That is what is the load on the engine. These 2 values are fixed. We are not going to change the amount of water supply to the engine as well as to the calorimeter. Let us look on to the time consumption for 5 cc consumption of fuel. Okay, this is what is the time consumed by the engine for the 5 cc consumption of fuel. Look on to the mercury manometer limbs difference, that is going to give us the air pressure, and this is the speed with which the shaft is running, and again we need to note down the difference, which is T5, T5, T4, T3, T2 as well as T1. These are the 6 temperatures that we need to note down. Now all the trials, all the experimental readings are being noted down. Okay, now we
have conducted the experiment. We have the tabulated values with us now. Let us look on to the tabular column. We have conducted 3 trials. Let us look on to one particular trial. I will be taking trial number 1, in which load spring balance on S1 in terms of kg is 6, on S2 is 3.25 kgs. This is the load which we have applied onto the engine, and these are the spring loads. Net load on the brake drum will be S1 minus S2. Since these two are acting in opposite direction, we will be subtracting one from other, so we will be getting 2.75 upon subtracting S1 minus S2. Next, we have noted down time taken for 5 cc fuel consumption. In terms of seconds, it is 25.81, and we have noted down the crankshaft speed, which is 1578 rpm. Mass flow rate of the fuel has to be calculated. Heat supplied has to be calculated. dP, IP, mechanical efficiency, brake thermal efficiency, and volumetric efficiency. All these terms from here, mass flow rate onwards, needs to be calculated. Till this is the observation from the experimental part. So for that particular trial, we have the calculation part over here. Let us look at the calculation now. First one is quantity of fuel used, which is nothing but the mass of the fuel consumed by the engine, which is denoted by MF, where we have fixed the XCC, the value of X is 5 for us. Specific gravity of the diesel 0.827 divided by 1000 into time consumption. 1000 into time consumed is 25.81. So mass of the fuel consumed by the engine is 1.6 into 10 to the power of minus 4 kgs per second. In the sense, per second, that much amount of kg of fuel is consumed by the engine. That is what we have written over here, 1.6 into 10 to the power of minus 4. That is the first thing. Next thing is heat supply. Upon burning of the fuel, what is the quantity of heat supplied by the burned fuel to the engine, which is given by Qs, which is equal to mass of the fuel into calorific value of the fuel. So mass of the fuel we have calculated in the previous step, 1.6 into 10 to the power of minus 4, and calorific value of the diesel is 43,400. So we will be getting 6.94 kilowatt as heat supply. Qs is 6.94 kilowatts. Next thing is BP, which is nothing but the brake power. Brake power is the power available at the crankshaft. So which is nothing but 2 pi n into torque divided by 60. This term is going to give us the torque. So here P is nothing but the S1 minus S2, which is nothing but 2.75. Load on the brake drum. P and radius. This is the observation from the brake drum, which is nothing but 0.15 meters into 9.81 into 2 pi n. 2 pi and speed is 1578 for first trial. So upon substitution, we have got BP, that is brake power, which is nothing but the power available at the crankshaft as 0.668 kilowatts. So BP is 0.668 kilowatts. Next thing is a specific fuel consumption, which is nothing but the amount of fuel consumed by the engine per kilowatt of power development. The formula is MF, mass of fuel consumed, divided by power developed, which is nothing but BP into 3600. We have calculated MF as well as BP, so we have substituted that, and upon substitution we have got the value, SFC value as 8.61 into 10 to the power of minus 4 kg per kilowatt hour. That we have not shown in the tabular column. Let it be. Next thing is frictional power. What is the amount of friction that engine is showing in order to develop this much power? That needs to be calculated. So frictional power has to be calculated for entire trials. We cannot calculate the friction for a single trial. We need to look on to the various aspects of the engine, and we need to take the frictional power for that particular speed of the engine. So this frictional power we have obtained as 1.8 kilowatts from the graph. This graph is nothing but Williams line or Williams method of extracting the frictional power from the engine. Let us look onto the graph. On the x-axis we have Pp, on the y-axis we have mass of the fuel consumed by the engine. For various trials, we need to plot the Pp. For that purpose, we need to, for that PP, power development, what is the amount of fuel consumed needs to be plotted. Upon plotting, we will come to know that this line is almost linear, and at zero power development, it is showing certain fuel consumption. So, certain fuel consumption is there over here for zero power development, and the curve is almost linear. It is allowing us to extrapolate the graph backwards. So, this curve, extrapolation curve, is going to touch the negative x-axis at certain point. From the origin, that particular distance will become the frictional power of the engine. Upon plotting the graph for various trials, this frictional power has been taken as 1.8 kilowatts. That is what we have written over here. So this 1.8 kilowatt is the friction occurred by the engine at that particular speed. Next, if you want the IP is nothing but the indicated power, actual power developed by the engine as soon as the fuel is burned, which is nothing but brake power, which is available at the shaft, plus frictional power, overall friction that engine is offering. If you add these two, we will get 0.668, this is nothing but this, plus 1.8 kilowatts. Upon substitution, IP is 2.468 kilowatts. If you clearly look onto the values, PP should be less than IP, because PP is the power available at the shaft, IP is the power developed inside the engine. Always power developed inside the engine will be higher than the power which is available at the shaft. So for our trial, PP is just 0.668 kilowatts, whereas power developed is 2.468 kilowatts. So whatever values we have got is correct. Next thing is I need to look onto the mechanical efficiency. What does mechanical efficiency says? Mechanical efficiency is nothing but the ratio of brake power to the indicated power. In the sense, brake power is nothing but the power available at the shaft. Indicated power is nothing but the power which is available inside the engine cylinder as soon as fuel is burned. So, from engine cylinder, the power has to be transmitted to the shaft through various mechanical devices. From the engine cylinder, it has to pass through connecting rod, then crank, then crankshaft. All these devices are going to offer certain resistance, and hence the power which is available at the end as a brake power will be less. So that is what is our mechanical efficiency. In the sense, our mechanical devices which are transmitting the power from engine cylinder to the crankshaft, how much efficient they are in transferring the power from one place to other. That is what this is going to indicate. So BP divided by IP. So we have got both the values. Upon substitution, our mechanical efficiency becomes 27.06% at that particular speed. Next efficiency is brake thermal efficiency, which is nothing but power developed divided by fuel supply. Heat supplied by the fuel. So BP is the power developed and QS is the heat supplied by the fuel. So BP is 0.668 for the first time, and heat supplied by the fuel is 6.94 kilowatts. So upon substitution, we will get the brake thermal efficiency as 9.61%. Mechanical efficiency is 27.06, brake thermal efficiency is 9.61%. Finally, we need to look onto the volumetric efficiency. Volumetric efficiency, as the name itself indicates, that what is the volume by which the engine is running. Engine cylinder is available with certain amount of volume, and if that volume is utilized completely for running the engine or not, that is what this volumetric efficiency is going to say. If you look onto the definition, actual flow rate is in the numerator, theoretical flow rate is in the denominator. In the sense, theoretical is the theoretical one, which is the ideal one, so which is in the denominator, which will be always maximum than that of the reality or actuality. If actuality becomes a reality, then volumetric efficiency becomes 100%. That never be possible in practicality. So Q actual divided by Q theoretical. Q actual, we have made use of air box over there. In the air box, we have orifice for the supply of air to the engine. Since it is a diesel engine, only air enters into the cylinder. So from this is the orifice of formula, and this is the cylinder area into stroke length. So this becomes the theoretical discharge that can accumulate inside the engine cylinder, and this is the actual discharge that is happening from orifice to the engine. If we divide these two values, we will get the volumetric efficiency of 79.5%. In the sense, among 100% availability of the volume of engine cylinder, 79.5% of volume is filled with air. So that is what is volumetric efficiency is saying. So this is what is first trial for us, wherein we have calculated mass flow rate for the first trial, heat supply, dP, IP, mechanical efficiency, brake thermal efficiency, as well as volumetric efficiency. If you look onto the performance curves, we have calculated all the aspects. SFC, we have calculated specific fuel consumption. BP, we are aware. Brake thermal efficiency, we are aware. Mechanical efficiency, we are aware. So, in order to plot the characteristic curves, what are all the variables that are required for us? All those things are calculated now. So now we can go for plotting of graph for all these variables. Before that, we need to make sure with a single value we cannot plot the graph. For that purpose, we will be looking onto multiple trials, where we will be increasing the load on the engine. In the second trial, 8.5, 3.5, and in the third trial, 10 and 3.5. If you look onto the overall load, it is getting increased. 2.75 in the first trial, 5 in the second trial, 6.5 in the third trial. So by varying the load or by increasing the load on the engine, we have calculated all these values. So now we need to look for the characteristic curves, which has to be a standard one. In the sense, you are very well aware of theoretical words of this particular graphs. By looking into the values or experiment what we have conducted, whether we are in the right manner or whether the engine is performing in the right manner or not, that has to be decided by these characteristic curves. So we have all tabulated all the values now. Let us look on to the plotting of graph now. Okay, now we have plotted the characteristic curves. The characteristic curves were SFC versus BP, brake thermal efficiency versus BP, mechanical efficiency versus BP. Let us look on to the curves. Let us look on to this curve first, brake thermal efficiency versus BP. If you look onto the curve, at the lower values of BP, the brake thermal efficiency is lower. At higher values of BP, the brake thermal efficiency is higher. In the sense, BP is directly proportional to the brake thermal efficiency. This can also be looked in this way. Brake thermal efficiency is defined as BP divided by heat supply. So BP is in the numerator. As BP increases, brake thermal efficiency also going to increase. In the sense, as power development increases, that particular efficiency, nothing but brake thermal efficiency, is also going to increase. So this is what is one of the characteristic curve. The second characteristic curve is mechanical efficiency versus BP. If you look onto the curve, mechanical efficiency is less at lesser values of BP, and mechanical efficiency is more at higher values of BP. So this is what the graph we have plotted by these values. If you look onto the mechanical efficiency, it is going, it is getting increased for increased values of BP. So that is what I have plotted over here. The reason behind this is mechanical efficiency definition is BP by IP. So in the sense, as power developed by the engine increases, it automatically says that mechanical components which are transferring the energy from one portion to other portion is also going to increase. That means mechanical efficiency is directly proportional to the power developed by the engine, which is nothing but the BP. And the last curve is SFC versus BP, where SFC is nothing but specific fuel consumption. Specific fuel consumption definition says amount of fuel consumed per kilowatt power developed. 1 kilowatt power development is going to consume how much fuel, is that is what SFC is going to say. So now if you clearly look onto the graph, at lower values of BP, SFC is very high. At higher values of BP, SFC is low. So now what we need to understand from this graph is, if I start the engine now, engine hasn't taken the momentum, engine hasn't reached its working condition. At that stage, the SFC, I mean fuel consumption to develop 1 kilowatt of power is very high. As you move on running the engine, as the power developed by the engine, once the engine takes the momentum, if you look on to the same 1 kilowatt power development, the specific fuel consumption is less. In the sense, fuel consumption by the engine goes on reducing as the engine gains the momentum. At the very initial state, it is higher. As engine runs, as engine reaches its normal temperature and normal operating conditions, the specific fuel consumption per kilowatt development of the power is going to reduce. That means these two are inversely proportional to each other. So very first graph is inverse proportionality, second graph is direct proportionality, third graph is also direct proportionality. So these are the characteristic curves that we were about to plot, and we have looked into those characteristic curves. In the next stage, we have to look for the energy balance that is happening in the engine. Okay, now here we are with the tabular column of heat balance sheet. Let us look on to the various readings. We have conducted 3 trials over here. So very first column is inlet temperature, which is denoted by the T2, outlet temperature, which is denoted by the T3, and mass flow rate in terms of LPM, which is MW1. All these readings are for cooling water, and calorimeter water readings, inlet temperature in terms of Kelvin, T2, and outlet temperature Kelvin, T4, mass flow rate LPM, and that means liters per minute, which is in terms of liters per minute, which is denoted as MW2, exhaust gas temperatures, inlet temperature T5, outlet temperature T6, and we are notating or we are substituting the values in terms of Kelvin, manometer reading H1 and H2 in terms of ml. So now here we are ready with the table. Now let us look on to the particular calculation which are required for drawing the heat balance sheet. So HW, which is nothing but difference of H1 and H2. H1 difference of H2, in the sense we need to add these two values. For first trial, upon adding, we will get 54 ml. Second thing is pressure head with which the air is entering into the cylinder. HA is nothing but rho W divided by rho A into HW. Density of water, density of air, mercury height, water height column. So upon substitution, the pressure of air with which it is entering into the cylinder is 45,000 meters of air. In the sense, it is in terms of meters of air. Mass flow rate of air, in the sense, what is the quantity of air which is entering into the cylinder, engine cylinder. Rho A, density of the air, area of the orifice, discharge coefficient of the orifice, square root of OG into HA, what we have obtained in the previous stage. Upon substitution, we have got mass flow rate of air as 6.94 into 10 to the power of minus 3 kg per second. Now, we are very clear, mass of the exhaust gas will be summation of mass of the air as well as mass of the fuel. So, mass of the fuel we have calculated in the previous stage, mass of the air now we have calculated. Upon summation, the value turns around to be 7.105 into 10 to the power of minus 3 kg per second. This is the mass of air that is entering into the cylinder. This is the mass of gas leaving out of the cylinder. If you clearly look onto the value, mass of the exhaust gas is higher because in this we have added mass of the fuel also. That is going to raise the value of mass of the exhaust gas. Next, heat carried away by the exhaust gases. What is the quantity of heat that exhaust gases are taking out is given by mCp delta T, where all the values are related to the exhaust gas. If you look onto the exhaust gas temperature, T5 and T6 are the exhaust gas temperatures. So mg, Cpg, T6 minus T5. This turns out to be 1.13 kilowatt. In the sense, exhaust gases are carrying the heat of around 1.13 kilowatt. Next thing is cooling water. What is the amount of cooling water? Cooling water heat absorption. QW is nothing but MW, CPW, T3 minus T2. Why T3 minus T2? So we are very clear that cooling water temperatures are T3 and T2. Upon substitution, this is the value we have got, 0.19 kilowatt. In the sense, 0.19 kilowatt of heat is absorbed by the cooling water from the engine. And finally, we were calculating unaccounted heat loss. Unaccounted in the sense, we cannot calculate few of the aspects, such as engine is going to radiate certain amount of heat and certain pumping losses will be there. All those things are to be measured with sophisticated devices. Those cannot be measured in the ordinary laboratory. That is why all those losses are included in unaccounted losses. So heat supplied minus BP, heat carried away by cooling water, and heat carried away by exhaust gases. If you operate this, you will get unaccounted heat loss as 4.952 kilowatts. So these are the few values which are required to draw the heat balance sheet. So now let us look on to the heat balance sheet. We can draw the heat balance sheet for individual trials. I will draw the heat balance sheet for one trial so that we will come to know whether the energy is getting balanced within the engine or not. Now let us look on to the first trial's energy balance sheet. Here we have drawn the heat balance sheet for the trial number 1. We have calculated heat supplied by the fuel to the engine, which is called as energy input, and we have denoted this as a QS. And the energy supplied by the fuel to the engine is 6.94 kilowatts, and we have considered that as 100%. On the left hand side, we have that much, which is nothing but the energy input to the engine. This supplied energy has to be utilized for various categories, such as to develop the power, which is nothing but BP, to cooling water, certain amount of losses will be there, which we have calculated as QW, and exhaust gases are going to carry certain amount of energy, which we have calculated as QG, and unaccounted heat loss, which we cannot measure with the help of the laboratory equipment, we have called it as QU. So that those are the energy expenditures, which is on the right hand side of the energy balance sheet. So on the left hand side, only energy input. On the right hand side, we have expenditure. BP is 0.688, QW 0.19, QG 1.13, and unaccounted QU 4.952. If we add all those things, it is around 6.930 kilowatts. If you look on the left hand side, it is 6.94 kilowatts. These two values are almost same. Next thing is percentage. If you want to calculate this percentage, divide this by this. So 0.688 divided by 6.94 will lead us to 9.62 percentage. 0.19 divided by 6.94, 2.73 percentage. 1.13 divided by 6.94, 16.28 percentage. And 4.952 divided by 6.94 will lead us to 71.35 percentage. If we add all these percentages, it is turning out to be 99.98 percentage, which is almost equal to 100 degrees centigrade. In the sense, in this heat balance sheet, the left hand side is almost equal to the right hand side. So because of that, we can say energy is balanced by the engine. This is the trial number 1's energy balance sheet or heat balance sheet. You can draw this heat balance sheet for trial number 2 as well as for trial number 3. In the same fashion, we need to look for balance of energy on either sides. So with this, we are ending up with our aim. What was our aim actually? We need to plot the characteristic curves for the 4-stroke diesel engine. Along with that, you are about to draw the heat balance sheet. We have looked into various curves as well as heat balance sheet. So this ends the experimental calculation as well as tabulation and then plotting the graphs. So now we will be looking into the few of the viva questions that may arise in this experiment. These are the few viva questions that we will look onto in this experiment. Namaste.